Welcome all to week 2 of probability. Last week we were looking at the chance of one thing happening. That was experimental probability. Now what we're going to be doing is looking at multiple independent events. What's the chance of this happening and this happening? So a couple different things happening at one time, or 3 or 4 or 5. So that's what we're doing this week, and we're going to look at the multiplication rule of probability. To start out, we're going to look at something simple. We're going to look at flipping coins. So, suppose you flip a coin once. What's the probability of getting a heads? Well, if you flip a coin, you could either get heads or you can get tails. Pretty simple. The chance of you getting a heads is 1 out of 2 possibilities. So it's 1/2, which is 0.5, which is the same as 50%. Pretty simple. You didn't need me to tell you that. But now what we're going to do is we're going to flip a coin twice. And I want to know what's the probability of getting both heads. Well, let's look at all the different possibilities we could get when we flip a coin twice. You could get a heads first and a heads second. You could get a heads first, struggling to write here, and then a tails second. Or you could get tails first and a heads second, or tail then tail. So there's 4 different possibilities, and the chance of you getting both heads is only one of them. So it's 1 out of 4. If you go on a calculator and divide 1 by 4, you get 0.25, which is 25%. So you probably don't want to sit there and draw out all the different possibilities, especially as we get to flipping a coin 3 times. So I'm going to show you a different way you could have done this. If we're flipping a coin twice and both of them have to be heads, I'm going to draw a slot here for each time that you flip a coin. The chance that the first one is going to be a heads is 1/2. And the chance that the second one is going to be a heads is also 1/2. And if I want to know the probability that both of those things happen, if both of them have to happen, all I have to do is multiply them together. So if I take 1/2 times 1/2, we end up getting 1/4, which is, as we saw earlier, 25%. So that's the multiplication rule of probability. If you have to have multiple things happening, just multiply them. So now let's go down and flip that coin 3 times. So I'm going to draw 3 slots here. I want to know what's the probability of getting all heads. So this has to be a heads, this has to be a heads, and that has also got to be a heads. The chance of getting a heads on the first one, 1/2. The second one, 1/2. The third one, 1/2. And we want to multiply these to find the probability of all of them being heads. And if you multiply them, we get 1/8, which ends up being 0.125, which is 12.5%. Now suppose we were going to flip this coin 4 times. What's the probability of getting all 4 heads? Well, I think you kind of understand what we're doing here. You could draw out 4 slots. 1, 2, 3, 4. And the chance of getting a head on the first one is 1/2. Let's just call it 0.5 this time. 1/2 and 0.5 are the same. The chance of the next one is 0.5. The next one, 0.5. The next one, 0.5. So we would multiply all of these together. Now there's a quicker way that you can do this. Instead of doing 0.5 times 0.5 times 0.5 over and over, you could just simply put it as 0.5 to the 4th power. And if we take 0.5 to the 4th power, we get 0.0625, which equals 6.25%. So if you flip a coin 4 times, the chances of you getting heads every single time of those 4 times, it's going to be about 6%. It's not going to happen very often, but it certainly could happen. So now what we're going to do is we're going to take the same information, and I want to know how many times would you have to flip the coin until the probability of getting all heads drops to smaller than 1%. So when we flipped 3 coins, it was 12.5%. When we flipped 4 coins, it was down to 6.25%. I want to know, how many coins do you got to flip to make it so the probability of all of them being heads drops to underneath 1%. So what we can do is we can just kind of use guess and check. Later in Algebra 2, you'll learn a much more efficient method of doing this. But we already know that if we did 0.5 times 0.5 times 0.5 times 0.5, we get 0.0625, 6%. Well, what happens if I add another one? This would become 0.5 to the 5th power. And you could see what that would equal. It's not going to be under 1%. Then we could try to the 6th power. And it's not going to be under 1%. And you can try to the 7th power. So if I take a calculator, and if I take 0.5 and I raise it to the 7th power, it becomes 0.5 to the 7th equals 0.0078. We'll round it to. And that becomes 0.78%, which is now smaller than 1%. So it would take 7, circle that 7. We'd have to flip that coin 7 times to make the probability of all heads become less than 1%. So what we've just been looking at is called the multiplication rule of probability. So a couple different rules on these is multiple independent events. To find the probability of both things happening, all you have to do is multiply. So to find the probability of both of them happening, for multiple things to happen, just multiply them. And then we get this thing called the complement rule. And the complement means it's not like, oh, you look nice today. Not that type of compliment. The complement rule in math is like the chance of something not happening. So let's say the chance of something happening is 30%. So this is going to be the chance that it does happen. Well, the chance that it doesn't happen would be 100 minus that 30%, which would equal 70%. So the complement is the chance of something not happening. So I'll put the word not happening. It's just kind of the opposite thing that happens. So the chance of it not happening, all you have to do is subtract it from 100%. And we're going to see some examples coming up. All right, first example here. We have Jessica's math teacher decides that for every time she turned in an assignment on time, she would get to spin the prize wheel. Now we're bribing students, I guess. It's not enough to just do it because it's the right thing to do. We're going to bribe this kid. So Jessica turns in 3 assignments on time. She gets to spin the wheel 3 times. She really wants a food prize. And there's a 40% chance of getting a food prize, those hot Cheetos. I bet she wants those hot Cheetos. What's the probability that she gets all 3 food prizes? That would be really, really lucky to spin it 3 times and get all those hot Cheetos. Sounds good. So we're going to spin it 3 times. So I'm going to draw out 3 slots. And this one has to get food, that one has to get food, and that one has to get food. So in order to find this probability, pretty simple. The chance of getting food on the first one is 0.4. So 40% as a decimal is 0.4. Then she's going to spin the wheel again. And whatever happened on the first spin doesn't impact the second spin. She still has a 40% chance of getting free food. So the second spin is 40%. The third spin is 40%. So what we do is we take all of these numbers and we multiply them together to find the probability of all of those things happening. So 0.4 times 0.4 times 0.4 is 0.064. And that would equal, move the decimal over 2 spots, 6.4% chance of that happening. So Jessica would have a 6.4% chance once she turns in those 3 assignments on time that she gets all 3 food prizes. So now we're going to go kind of the opposite way here. This is going to be called the complement. So now she's going to spin the wheel. She wants these food prizes, And now the question's asking, what's the probability she gets no food prizes at all? She's going to be disappointed. She did all that work, turning in her assignments on time, doesn't even get a hot Cheeto to show for it. So we're going to spin the wheel 3 times. And I'm going to say not food. We'll just say NF. Not food and not food. So this is like her getting shut out from all the food prizes. So if there's a 60% chance or a 40% chance of getting food, the chance of not getting food is 60% chance of not getting food. Remember, this is the complement rule. If something has a 40% chance of happening, then it has a 60% chance of not happening. So if we're going to have her get shut out, it's a 60% chance here, a 60% chance here, and a 60% chance there. And we can multiply all of those together. And if we take 0.6 times 0.6 times 0.6, it equals 0.216, which is 21.6% chance. She has a 21.6% chance of getting no food prizes at all. Chances are she might get 1 food prize, or she might get 2 food prizes. Probably not going to get all 3 food prizes very often. So go ahead, pause the video now, and you're going to learn about Jeremy growing onions on top of his roof garden. Pause the video, try those. You'll submit those as a quiz later on, and then come on back for the last example. All right, we have Jamaria finishing her ACT test, and there's 3 questions to go. Time is almost up, so she's just going to randomly fill in some questions or some answers here. Doesn't have enough time to actually try them, just wants to make sure she's got a guess in there. So here's a sample question if you want to. I don't know the answer to that. It's not a math question. So she's got 3 of them to go. I'm going to draw out 3 slots. We're going to make 3 guesses. And there's 5 possible answer choices for each question. What's the probability that Jamaria gets all 3 questions correct? So there's 5 answer choices on every question on an ACT, but only 1 of them's correct. So the chance of getting it correct is only 1 in 5. You got a 1/5 chance of getting that correct. Then you're going to go to the next question. You're going to guess again, and you again only have a 1 in 5 chance of getting it correct. And the same for the last one. You have a 1 in 5 chance of getting it correct. And to find the probability that you get all of them correct, we're just multiplying. Now, if you don't like fractions, just turn them to decimals. This is 0.2, 0.2, and 0.2. So if we take 0.2 times 0.2 times 0.2, we end up with 0.008, which is 0.8%. It is smaller than 1%. So if you've got 3 questions to go on the ACT, you're probably not going to get them all right if you just guess. It's less than 1% chance of happening. All right, last example. Again, finishing up that ACT, I want to know what's the chance that she gets all 3 of them incorrect. What's the chance she gets them wrong? So out of these 5 answer choices, there might be one of them that's correct. I don't know if that's the right one, but that means 4 of them are wrong. She has a 4 out of 5 chance of getting them wrong. So we're going to draw 3 slots. The chance she gets the first one wrong is 4 out of 5. The chance the next one's wrong, 4 out of 5. And the chance the last one wrong, 4 out of 5 again. They're independent events. Whatever happens on the first one doesn't impact the next one. To find the probability of all of those happening, we just multiply. Again, you could turn these into decimals. So 4/5 is the same as 0.8. And if we take 0.8 times 0.8 times 0.8, we end up with 0.512, which is just a bit over 50%. It's 51.2% chance that she gets them all wrong. So go ahead and try the next couple on your own. Make sure you understand it, and then we'll focus on tree diagrams so you can better visualize it in the next lesson. So go ahead and submit these, and then come on back for the next lesson.